You know, when you flip a light switch, it feels so simple, right? Almost effortless. But behind that one little switch is one of the biggest, most complex machines on the entire planet. It's a network the size of a continent, where thousands of huge power generators all have to spin in perfect, unwavering synchrony. Today, we're going to pull back the curtain on this hidden symphony of the power grid.
This quote just perfectly nails the high-stakes balancing act that's happening 24/7. See, the power grid isn't just a bunch of wires. It's more like a living, breathing system that operates like a perfectly timed orchestra, and if just one musician is out of step, the whole performance can come crashing down.
All right, so to really understand this orchestra, we have to start with its tempo. In the world of electricity, this tempo has a very specific name, and it is without a doubt the single most important vital sign of the entire grid.
To get a feel for the grid's rhythm, first we got to talk about the kind of electricity it uses. Now, you know the power you get from a battery, right? That's direct current, or DC. It just flows in one steady direction. The power grid, though, runs on something totally different, alternating current, or AC. This means the electricity is always pulsing back and forth, creating this perfect, smooth wave.
And the speed of that wave, well, that's everything. That speed is called frequency. It's measured in hertz, which is just a fancy way of saying cycles per second. This is the steady, unwavering tempo of our electrical symphony. It's the beat that every single power plant, from a huge nuclear reactor to a tiny solar farm, has to follow absolutely perfectly.
Now, you might be surprised to learn that the whole world doesn't march to the same beat. The grid is mostly split into two main tempos. Here in North America, our grid pulses at 60 times per second. That's 60 hertz. But in Europe, Asia, and most of the rest of the world, it's 50 hertz. And look, the exact number itself isn't the most important part. What's absolutely critical is that this number has to be kept incredibly stable with almost zero wiggle room.
So you gotta wonder, why those specific numbers? Why not 10 hertz, or maybe 100? Well, it all boils down to a really clever engineering trade-off. See, lower frequencies actually lose less energy when you send power over long distances, but higher frequencies let you build smaller, more efficient transformers. It turns out that 50 and 60 hertz were the perfect sweet spot, a great compromise for building a practical grid that could span a whole continent.
So frequency acts like the grid's real-time speedometer. It tells us everything about the balance between the electricity we're generating and the electricity we're all using. If power plants, the supply, are making more power than we need, the frequency starts to rise, just a tiny whit. If everyone turns on their air conditioning at once and demand shoots up past supply, the frequency drops. Grid operators work around the clock 24/7 to keep that scale perfectly balanced and lock that frequency right on target.
Okay, so if the entire grid is this one massive synchronized machine, how in the world does a new generator, a brand new musician, join this orchestra without causing total chaos? Well, it's a process called synchronization, and it has to be absolutely flawless.
It's a really delicate dance, and involves three absolutely critical steps. First, the plant operators have to spin their generator up to match the speed, that 60 hertz frequency of the grid. Second, and this is tricky, they have to align the wave, making sure the peaks and valleys of their generator's electrical wave line up perfectly with the grid's. And finally, at the exact split second of perfect alignment, they close the breaker and connect to the grid.
And this is where something incredible happens. The instant that connection is made, these immense electromagnetic forces just take over. They literally grab the new generator and lock it into step, magnetically yoking it to thousands of other generators across the country, forcing it to spin in perfect unison with the entire continent.
Now that powerful magnetic lock-in is what keeps the whole system stable, but it also creates a huge vulnerability. So what happens when one of those musicians suddenly, without warning, just drops out of the performance?
This is the nightmare scenario that keeps grid operators up at night. Imagine a single, massive power plant, maybe powering an entire city, suddenly trips offline. It just disconnects. What happens in that split second?
Well, in an instant, all the power that generator was making is just gone. But the demand for that power, all the lights, factories, and TVs it was running, that doesn't disappear. So right away, you have this immediate and really dangerous imbalance across the whole grid. Demand is now way, way bigger than supply.
And all of that electrical demand has to go somewhere, right? It instantly floods onto the nearest neighboring power plants, but they might not have the extra room to handle that sudden surge. So now they're overloaded, and their own safety systems might trip them offline to keep from being damaged. This just makes the imbalance even worse, pushing an even bigger problem onto the next set of generators. It's a domino effect, a chain reaction we call a cascading failure, and it can black out an entire region in just a few seconds. The symphony just collapses into silence.
To stop that catastrophic domino effect, grid operators have one last, desperate tool in their toolbox. It's called under-frequency load shedding. If the grid's frequency, its heartbeat, drops to a dangerously low level, automated systems will start intentionally cutting power to entire neighborhoods. It's a really painful decision, kind of like a conductor being forced to silence the entire violin section, but it's done to cut demand, get things back in balance, and save the entire performance from a total collapse.
You know, for over 100 years, this electrical orchestra has been made up of very similar, very predictable instruments. But that's all changing. New types of musicians are joining the band, and they play by a completely different set of rules. So let's compare the old players with the new ones. Traditional power plants use these massive, heavy turbines and generators. I'm talking hundreds of tons of spinning steel. Renewables, like solar and wind, connect to the grid through these high-tech electronic inverters which have no big moving parts. And this difference brings up a really, really critical new challenge: inertia.
Think of it like this. All that spinning metal in those traditional plants acts like a giant stabilizing flywheel for the whole grid. It has physical momentum. This property, inertia, naturally resists any sudden changes in frequency. It's a built-in shock absorber that has kept our grid stable for decades.
But here's the thing. Solar panels and wind turbines don't have this massive rotating mass. Their inverters are incredibly fast and smart for sure, but they don't contribute any of that physical inertia to the system. So as more and more of our power comes from these sources, the grid loses its natural shock absorber. It becomes more brittle, more fragile, and a lot more sensitive to any disturbances.
And this really brings us to the central question for the future of electricity. The old symphony of a few dozen massive heavy players is being replaced by a new one with millions of smaller, lighter, and faster electronic musicians. So the challenge we're facing now is learning how to conduct this new modern orchestra to make sure the lights always stay on and the music never stops.